Greetings to everyone. Myself Chintan Manyar from the Indian Institute of Remote Sensing, Photogrammetry and Remote Sensing Department. I'm a second year MTech student specializing in satellite imagery analysis and photogrammetry. Today I will be presenting a paper on generative adversarial network for cloud removal from optical temporal satellite imagery. Whenever we talk about remote sensing, the clouds in the Earth's atmosphere are imminent. While they provide important information about the climate, meteorological data, and weather conditions, they are an obtrusion when we talk about optical remote sensing and when we want to observe the ground features. This has been a prominent problem in the field of satellite remote sensing, and several methods have been proposed to deal with this problem. Some of them are spatial methods, which involve interpolation and kriging and other such statistical means to replace the cloudy pixel in an image from information from the surrounding pixels. Then there are spectral methods, which work on the idea of higher wavelength bands penetrating more than the lower wavelength bands. Sometimes even SAR images are used to fuse with the optical image for cloud removal. Then we have temporal methods. These work on the idea of replacing a cloudy pixel with a non-cloudy pixel of an image which is temporally close of the same region. Then we have deep learning based methods. Recently, artificial intelligence has pushed through in the remote sensing applications, and deep learning based methods have been very promising in cloud removal. One such deep learning method is called generative adversarial network, which has shown very promising results. So a generative adversarial network is a combination of two deep neural networks, the generator and the discriminator. The generator takes random noise as an input and generates a fake sample. The discriminator has to discriminate between the fake sample and the real sample. These samples are from the dataset. As we train the entire GAN network, the generator becomes more and more good at producing these fake samples, and eventually the discriminator is no longer able to differentiate between the real and the fake sample. This is when we say that the training of the GAN converges. Now we shall see how GANs have been used and can be used for cloud removal in satellite imagery. So the objectives of the study are to explore the capability of a Pix2pix GAN, which is a specific GAN model for this cloud removal purpose in temporal optical satellite imagery. Pix2pix GAN has been previously used a lot of times for cloud removal, but it has always been used in conjunction with higher wavelength data such as SAR. In this study, we uniquely try to train this model solely on multispectral data, and we also try to investigate the robustness of the model when it is trained on a minimal small training dataset. So more about the Pix2pix GAN. As the name suggests, it is a pixel-to-pixel translation model, and it is a paired image translation model. It means that as an input, it takes a pair of images, which is true and false. In our case, the true image is the cloud-free image, and false image is the cloudy image. The job of the model is to translate the false image to true image at pixel level. So it translates cloudy image to cloud-free image at pixel level. These are the architectures of generator and discriminator used in the Pix2pix GAN. So we chose Patiala region of Punjab as study site, mostly comprising of paddy fields, and a few urban patches were there. And then we used Sentinel-2 data at 10-meter resolution. Since it is very frequent, highly temporal, we were able to get the cloud-free image at 27th October and the cloudy image just after 2 days on 30th October. The methodology was as follows. With the true image as the cloud-free image and false image as cloudy image, we created an image batch size of 1024, and then we cropped both the images. Then we augmented the images by applying 4 rotations. So we had 4 unique images. Then we stacked them iteratively 10 times. So we had a data set of 10 true and false image pairs, which we used to train the Pix2pix GAN model. Then we generated the test data set. We took some actual cloudy images, and then we took the cloud-free image, and then we generated fake cloud cover using Perlin noise. Then we tested the GAN model, and then we evaluated the GAN model using certain metrics. So these are some training details. We trained the model up to 1200 epochs. This is the graph of the discriminator loss and the generator loss. So this is the discriminator loss. It is actually sum of real and fake loss, and the generator loss is as described over here with the weighted L1 score. So these are the results of our model. The first row indicates the source, which is the actual cloudy images, which are the input to the model. The second row indicates the output of the model, which is the cloud-free images generated by the model. And the third row indicates the actual cloud-free image for the exact same region of the image. So we can see by comparing these two rows that the model did pretty well in removing the cloud cover. However, in some cases, it adapted to the dark shadowy regions, and there was some minor contrast issue in the generated image. To evaluate the model performance, we have used qualitative analysis as well as comparative analysis. So we have used Pearson correlation to evaluate individual bands of the generated image. This also shows the direct correlation between the DN values or the pixel values of an image. So we can see how correlated the DN values of the target image and the generated image are. So again, this is the input to the model, this is generated by the model, and this is the actual cloud-free image. We can see that NIR band showed correlation of 68%, red showed around 47%, and green around 40%. It is natural as we move from higher wavelengths to lower wavelengths, the penetration will decrease, and hence the correlation will also decrease. We also use the peak signal to noise ratio to record the information gain. For this, we took the PSNR of the input image, cloudy, with the actual cloud-free image, and then we took the PSNR of the generated cloud-free image and the actual cloud-free image. This indicated that almost 20% information increased. From PSNR 13%, it went to PSNR 34%, and the model was able to increase 20% of the information in the image. Then we also used a metric called structural similarity index to gauge the brightness, contrast, and structure of the images, and it was maintained up till 95%. Finally, to do a real-life evaluation of the generated image, we performed one of the most common tasks in remote sensing, which is line cover classification. So we took the cloudy image, generated cloud-free image, and the actual cloud-free image for the same region, and then we performed SVM classification for 4 classes, which are indicated over here. And here are the accuracies of those. So source is the cloudy image, which gave an accuracy of 41%. So it is not fit to use in real life. But if we give the source image to the model and the model generates a cloud-free image and then we classify it, then the accuracy shoots up to 84.6%. And then when we classify the actual cloud-free image, the accuracy is 92.6%. So the closeness of the accuracy in the generated and the target image shows that the model is good for real-life use cases of remote sensing. In conclusion, in this experiment, we used the Pix2pix GANs for cloud removal. The highlights are, we trained the model for a patch size of 1024. Almost all previous studies have trained on 5 and 2 cross 5 and 2 at maximum. We also train solely on multispectral data, and then we train on a very small data set which is augmented from a single image pair. Under all these conditions also, the model performs very decently and successfully removes the cloud cover. And on evaluation for real-life utilities, the model shows good results. Thank you.